In this video, we are going to discuss differentials. And what are differentials? Differentials are a device that we use to approximate functions, okay? That being said, what is exactly differential? So let's write a function y equals f of x. And then we know that the derivative is dy dx equal f prime of x. Okay, and now this is the derivative, the way we are used to see. And now I'm going to do something that is going to look a little strange. Okay, I'm going to write the differential dy that is defined as f prime of x times dx. Okay, it looks like I took the dy dx and just treated it as a fraction and split it in two parts, dy dx. Okay, that's not exactly true because dy dx is not a fraction, it's just a notation. But let's bear with me for a moment. So let's understand this formula. This is the definition of the differential dy. Okay. So in this formula, x is an initial input. Okay. The x is a small change in the initial input. Let me move all this over here. There we go. Okay. And then dy. What is dy? dy is an approximation to the resulting change in the output. So what is happening here? The differential dy, that is f prime of x dx, is telling us how to approximate the change in the output when we have a small perturbation of the input. Let's do a picture to understand that. But this is very useful in reality because sometimes when we try to apply math to engineering, for example, we can write down our model and be sure that things will happen in a certain way, but then our measurements can be off by a small error. So this differential is telling us, depending on how off we are from the actual measurement, how off we will be after the experiment compared to our predictions. Now, I was saying, let me, with a picture, explain geometrically what we are doing. So let's say we have a function here. This is our f of x. And let's say we work at this point, x f of x, okay? And here, of course, we can take the tangent, okay? And now, let's say we move from that x some distance, and this distance, we can call it the increment in x, or we can just say that is the dx, the small change in the initial input. And now what we want to know is what is the change in the output. Okay, so if I move from x to this other point, that is x plus an increment plus an error, the value of f at this point is here. Okay, you see the red dot? So it's not exactly the same as the value of f of x. So when we have an error in the input, we will have an error in the output. Okay, there is a difference in the input that translates into a difference in the output. That difference in the output is the increment of y that is approximated by the differential. But the differential is actually this distance here. So this is dy. Okay, so in this picture, everything is really big. So it may not look like a great approximation, but if this picture, if I repeat it for a very small increment of x, then you will agree with me that the difference between the dy and the increment of y is going to be minimal. I cannot almost see the difference in the picture, okay, once I zoom in. All right, so let's compute some examples and see why would anybody choose to do this in reality. So let's say we have the function, some experiment. After some experiment, we arrive to the conclusion that we have our variable x that can be any quantity you want. That's your input, and the output is given by this function that is a polynomial of degree 3. Okay, and now you are interested in knowing, in comparing what is the increment in y and the differential y. Okay, when x changes from, let's do 2 examples. It changes from 2 to 2.05, and it changes from 2 to 2.01. Okay, I want to show you that the smaller the difference, the better the approximation. Okay, so what we are doing here, so we are expecting that in our experiment we think we are measuring 2, but actually, because our instruments may not be very precise, we are measuring 2.05 or 2.01. Okay, and we want to know, even if there is some error in the measurement, how far will we fall from the actual conclusion that we should be observing. Okay. All right, so let's do A first. So when we want to compute the increment in y, this is simple, is the difference, let's see the picture again, is the difference in value of f at the beginning and at the end. Okay, so f at 2.05 minus f at 2. And we just need to compute this. It's going to be a little 2.05 to the power 3 plus 2.05 to the power 2 minus 2 times 2.05 plus 1 minus 2 to the power 3 minus 2 to the power 2 plus 2 times 2 minus 1. Okay. And this will take some time. We need to punch these numbers in the calculator, and we get 0.717625. And I'm writing all the decimals because I want to see how good the approximation is. Okay. All right. So now dy, the definition is f prime of x times dx. And here there are two things that we need to figure out. What is x? So given the problem, we are saying that we change from 2 to 2.05. So x, we are going to pick 2. And then the dx, this is equal to the increment. So this is, let me write it. Dx is the increment in x, the input, the difference in the input, sorry. So this is 2.05 minus 2. That is 0.05. And then the derivative, I can just compute it. So this is 3x squared plus 2x minus 2 times the dx, which is 0.05. But x, I said it was equal to 2, so let's write that. Okay. And we can compute this. And what do we get? So I got 0.7. I can actually write it here. Okay, so you see here the approximation. It's approximating up to the first digit. Okay, so it's not bad. We were off, the input was off by 0.05. The output is going to be okay up to the first digit. Then after that, there's going to be a little bit of error. That's what I'm trying to say. Now part B says to do the same thing, but now 2.01 instead of 2.05. So the increment in y, that is just as before. Now, the disadvantage of computing the actual increment is that even for a polynomial that is kind of easy, it's a lot of computation. There is very little that we can recycle. Okay, we have to repeat the computation several times. Okay, so in this case, what I got was 0.140701. Okay, so here we have to do lots of computations, and if we have to repeat the computation 2 times, it's a pain, but if we have to repeat it 100 times or 100 different measurements, it's really unbearable. Let me show you that actually the differential does much better. Because again, since we are working around x equals 2, okay, the f prime of x, this we computed once and we can use it again. It's the same as before. And then the dx is the increment, which is which is 2.01 minus 2, 0.01. So you see that this is actually a machine. Oops. So we have here. So we have this quantity here that we are computed once. And now we can use it again and again and again. And we just need to multiply by the error in the input every time, okay? So if I want to repeat this for 2.03, I will write here right away 0.03, that's it. Okay, so it becomes much more practical. Yeah, and then when I compute this, I get 0.14. Okay, so in this case, actually we got, because we were closer, we got 3 correct decimal digits almost. Okay, 0.14 is correct. Then we will be off after the 3rd digit.